We begin by introducing something that statisticians call the cumulative distribution function. It is, quite simply, the percentage of the data equal to or less than a given value. A simple example will illustrate. Let's suppose I've got data on the number of times a student falls asleep in class, and that so far 42% of the class has not yet fallen asleep, while 43% of the class has fallen asleep once, and the remaining 15% have fallen asleep twice. Here's a table of the data. Remember, the cumulative distribution function is the percentage of data equal to or less than a given value. And so, 42% of our class fell asleep 0 times or fewer, while 85% fell asleep 1 time or fewer, the 42 plus the 43, while 100% fell asleep 2 times or fewer. We can, of course, draw a picture. We'll put number of times falling asleep on the horizontal axis, the frequency, probability with which it occurs on the vertical axis, and to begin with, you'll note that nobody falls asleep a negative number of times. But once we hit 0, 42% of the class has fallen asleep 0 times or fewer. What's more, 42% have fallen asleep 0.1 times or fewer, or 0.2 times or fewer, and so on up through 0.999999999 times. But once we hit 1, the function jumps. 85% have fallen asleep 1 time or fewer, 1.5 times or fewer, 1.99999 times or fewer. And then at 2, it jumps again. 100% have fallen asleep 2 times or fewer, 2.5 times or fewer, 2.846 times or fewer, and so on. Again, fairly simple concept. Let's look at it in a somewhat more involved situation, the normal distribution. What can we say about the cumulative distribution function for the normal? And in particular, we'll look at the standard normal distribution, mean of 0, standard deviation of 1. And so, for the standard normal, what percentage of the data have a z-score of -2 or less? In other words, we're asking, what's the cumulative distribution function of a standard normal at a z-score of -2? We will, of course, draw a picture. We're looking for the red shaded area, the area from -2 on down. And an Excel function or a table will tell us that that area is 0.0228. In other words, for the standard normal, the cumulative distribution function, the CDF of -2, is 0.0228. Another example, what's the CDF of +1? How would we find that? We want the area from 1 on down. Norm.s.dist of 1 is 0.8413. That's the CDF of 1 for a standard normal distribution. And we can do this for any value in a normal curve. In practice, you'll just do it for a bunch of them and then connect the dots, so to speak. And we'll get a picture that looks like this. 3 standard deviations down, virtually none of the data should be further down than 3 standard deviations. 2 standard deviations below average, we worked that one out, that was 0.0228. Fairly rare for a data point to be 2 or more standard deviations below average. As we get closer to the middle, things will climb, until right at the middle, we should have half of the data from the middle, the mean of 0, on down. For one standard deviation, it was 0.8413, and so on. Virtually all the data will be 4 or fewer standard deviations from the mean. This is our graph of the cumulative distribution function of the normal curve. So in summary, the CDF, or cumulative distribution function, gives the percentage of data equal to or less than the various data values. And it gives us another way that we can draw a picture of our data.